Okay, great, thanks. Hi, Nancy. This is David in Barrow. There we go.
Hi, David. How are you?
Doing well. We're ready to go. Sorry about the technical difficulties, but we should be all set.
Okay. Do you want me to start then?
Please.
Okay, perfect. Well, thank you, everybody, for joining. I am assuming that everyone can hear me, so I think we have someone joining from Cooper's Landing. Are you able to hear me? Wave if
we
you're
can hear
able
you.
to hear.
We're good.
Great. Thank you. And how about Dillingham? Can you hear me? I think Dillingham's out. Okay. And Eagle, can you hear me? Great. And Craig, can you hear me? Just wave if you can.
Wave.
Craig can hear okay? Okay, perfect. All right. Well, thank you very, very much for attending today's talk. Obviously, this is a little test of our capabilities to talk between New Hampshire and Alaska, and hopefully this will all work. But please bear with me. If you do have a question for me while I'm talking, please just unmute your video, and then I'll be able to hear you, okay? And I'll stop at any point and try to answer your questions. Let's show the slide. The point of today's talk is really to be the first of what David and I thought might be an interesting series of talks on crude oil and on how crude oil behaves in water, and so that maybe it will help us to be able to discuss some of the issues that you feel that you're facing in the state. I thought you might want to know a little bit about my background first before I started talking, and then a little bit about how this series developed, and then a little bit about the goals of this series of talks. And this week, what we're going to do is concentrate on the first of two questions. What is crude oil? And how do we characterize it? Now, there have been books and books and books written on this topic, but I'm going to try to condense it down into a series of characteristics and things that are going to be important for us to understand about crude oil, so that we can think about how it behaves when it gets into water. So next week is when we'll actually talk about what happens when crude oil gets into water. But this week, we're going to have to just kind of get a little bit of background about some of the important characteristics of crude oil, so that we can think about what actually might happen. So bear with me, and if you have questions, just stop me. I'm happy to stop any place along the way. But let's start for a minute with my background. Let's click off the slides for a minute. So my name is Nancy Kinner, and I am a professor at the University of New Hampshire, and started out years ago when I was an undergraduate studying marine science, marine biology, and then after I graduated from college back in 1976, started to think about how I wanted to be solving environmental problems, and decided at that point to go back to school and learn about environmental engineering, which I did, and got my PhD. And over the course of my career since 1983, when I got my PhD, I have done a lot of work on various aspects of gasoline and fuel oil and things like that. And back in the early part of the last decade, around 2002, the University of New Hampshire got approached by the National Oceanic and Atmospheric Administration, NOAA, because NOAA has a group within it, big NOAA, that looks at oil spill response and restoration, and also what is the science behind oil spills. And they came to the University of New Hampshire because we have a big marine science program here, and we also have a big environmental engineering program that looks at cleaning up various kinds of spills. And they said, let's start a center here to look at oil spill response and restoration and what kinds of research needs to go on. So we did, and we actually have two centers here now, one that is funded by NOAA and one that is receives funding from a variety of other sources. And we have been for the last since about 2008, thinking about Arctic oil-related issues. And in 2008, we had a workshop here in New Hampshire thinking about different scenarios where we could have problems in the Arctic with ships sinking and all sorts of things, and how would we respond to them, and what were the research and development needs we really had with respect to some of these questions. And that grew into a series of workshops that we had in Anchorage looking at oil spill issues. And when we were in Anchorage, we were only able to bring a few people down from the North Slope Borough and the Northwest Arctic Borough to our meetings. And when we were there, those representatives from the North Slope Borough and the Northwest Arctic Borough said, you should really come up to Kotzebue and Barrow and run some workshops up there. So we did, and we just finished a workshop in Barrow in November, which was held at the Heritage Center and Tuzzy Library. And then we held one in Kotzebue earlier in the year. So this series developed when we were in Barrow, and we were working in some of our breakout groups were in the Tuzzy Library, and I met with David, and he said, we've started talking about doing a series like this and decided this would be a good thing to try with a video connection. So here we go. Again, the whole point here is to understand crude oil and some of its characteristics, and then next week to think about how crude oil might behave in water once we understand its characteristics. So the goals of this series are really to give all of us kind of an equal footing to think about what the characteristics of crude oil are, and then think about how oil behaves in water, so that we're able to converse with all sorts of folks and to actually look at some of the literature that's been published with a more critical eye. So this week we're going to start talking about what crude oil is. Are there any questions at this point? Okay, doesn't seem like there are any questions, so I'm going to go on. So let's go to the slides. So first, perhaps we got to put this in context and think about the fact that there are basically a couple of types of large spill scenarios for the Arctic. For oil. One is shipping, and the other one is drilling. And if we think about shipping, there are lots of different spills that could occur from shipping, anywhere from barges to bulk carriers of ore, cargo and container ships which have fuel oil on them, oftentimes just to power them, tankers, and cruise ships. And many of you may be familiar with a report that came out in 2009. It was the Arctic Maritime Shipping Assessment, AMSA, and this slide is from the AMSA report. And you can see here, this area that I'm circling is Alaska, right up there. So that's Alaska. And these yellow lines that you see are ship tracks in the year 2004 that occurred just in 2004. And you can see, not surprisingly, that there are a lot of ship tracks up here through into the Bering Strait. And you very well know that there are several ship tracks over here along your coast where barges come in, for example, to bring in the summer fuel, etc. This slide here is also from the AMSA report, and it shows for 2004 the barge traffic, just the barges and tugs. And again, not surprisingly, here's your area right in here, and you can see the tracks of the barges that have brought various commodities and fuel to Alaska. Now, this slide is also from the AMSA report, and the little dots that you see there are showing accidents and incidents that have occurred in the Arctic between the period 1995 to 2004. So these are the Arctic shipping accidents that have occurred, okay? And what's really amazing about this is that there isn't very much activity. In fact, there are no circles that you can see here right off the northern coast of Alaska. So it's been a relatively accident-free area, and that's the good news. Obviously, other areas, for instance, south of the Arctic Circle by the Bering Strait, etc., and over more towards Canada and down by Iceland, and also over here by Norway where there's a lot of drilling activity occurring. Those are areas where we've seen more incidents. The other obvious source of accidents and oil release into the Arctic is from drilling. And most of you probably are aware that petroleum was formed as a result of various sea life, plants and animals dying, getting buried under sediment on the seafloor, pressure, temperature, etc., creating petroleum. And if you look at many of the compounds that are in cells, they have these ring structures, many of these ring structures that I'm going to show you in a minute that are in crude oil. And there are some excellent references that you can read if you're interested that show how those biological products under high heat and pressure have actually become the products that the compounds that we see in crude oil. So the drilling occurs, and one of the interesting things that I always find amazing is how do you, even when you see these estimates of how much oil is in the Arctic and under the ocean, etc., how do they actually do that? And I thought it might be worth a little bit of an aside here to show you how some of that works. So lots of times in an aquifer, they'll drill down and they'll hit oil. In this case, in this lower layer here, and that's called a proved reserve, okay? So you know you've hit the oil. Then if they drill a second well, they can say now, okay, between these two wells, we know we have a certain amount of oil, and they can project or estimate, scientists can estimate, particularly in this country, folks from the U.S. Geological Survey, can estimate what the potential might be for other oil in the reserve. And then, of course, if they start drilling dry holes, they know where that reservoir ends. But this is really complex stuff, and I'm not going to go into it in any great detail, but there's a lot of work that's involved in making some of these estimates and looking at the geology and predicting what might be there as well. The other thing I want to mention, because when we talk about spills in the Arctic, especially from shipping, we're going to be talking about different fractions. And so when crude oil comes out of the ground, it actually gets refined. And the refining process is really just a distillation process. So basically what happens is the crude oil is put into a tower, and what happens is that the various fractions or various parts of the crude oil, the different compounds that I'm going to show you in a few minutes, come off at different temperatures. So the gas, the LPG, comes off at a very high temperature. The gasoline, it also comes off at a fairly high temperature. And these are a function of the boiling points of the different compounds that are in the gasoline. So you can see here along the side that we have asphalt is really, really heavy. It's kind of the residual material. It has the compounds in asphalt have very, very high boiling points. And so it's going to be that thick, gloppy stuff that we know that is used to pave roads. And then you see other materials that get progressively lighter and lighter, and they are the fractions that boil off at lower and lower temperatures. So if we think about this, this is the low temperature boiling points for these products. And this is the highest temperatures. These things really don't boil until you heat them up to 1,000+ degrees. So you really need high temperatures. So there are all these different fractions, and any one of them could be involved in an accident for a spill. Just to give you an idea about from a given barrel of oil, and a barrel of oil is not a 55-gallon drum here. It's approximately 44 gallons, okay? About 44 gallons or so in a barrel. And you can see that most of what comes off is, that gets distilled off is gasoline. Obviously, we use a lot of that. There's jet fuel that comes off. There's diesel, heavy fuel oils, and some of the gases. So these are the fractions that we tend to use and the products that are made from a barrel of crude oil when it's refined. I'm not sure how many of you have actually seen North Slope crude. If we zip in here a little bit, you'll be able to see I have here a couple of vials of North Slope crude for you. This stuff is actually not very thick. I don't know if you'll be able to see this all that well, but I'm going to pour a little bit of it into this cap. And you can see it pours relatively easily. Is that as close as we can get? Let me just try coming a little closer to the camera. I really want you to see this. So I'm going to try coming a little bit closer. Here we go. Okay, you can imagine what it's like to be in my class. Maybe this isn't in focus, but let me just show you. So this is it pouring right here. See it? It's relatively liquidy, okay? This crude here actually happens to be the North Slope crude, okay? And it's nice and black, typical of what we would see for a crude oil, okay? This vial looks exactly the same, but it's a Norwegian crude oil. This is called a Statfjord crude oil. And this oil is a little bit different, but it looks just the same. If I were to show you crude oil from the Deepwater Horizon well, it would look very much the same. But here's the important fact. Crude oil is very, very different from well to well, okay? So let's think about this. What do you mean by very different, Nancy? Well, if we drill into a reservoir of oil, and you drill two wells into that reservoir, those two wells will have slightly different characteristics potentially in the oil that comes out of them. As you drill a well and then pump that well over time, the oil will also change in character. Okay, so when you're in a well that's freshly drilled, your characteristics of the oil tend to change over time. So it's not, the thing I want you to remember about this is that crude oil is not a static thing, okay? It's changeable. And what we need to understand is that the material that gets spilled, the type of crude that gets spilled, will dictate how that spill, how that actual response goes and how that oil that's spilled behaves in the environment. So this is why I think it's really, really important that we talk a little bit about the composition of crude oils so that we understand what we're talking about when we come to how oil behaves when it reaches a water body or gets spilled into a water body. So any questions so far? No questions. Okay. All right. So let's go back to the slides and we'll talk a little bit about crude oil composition. Okay? This very strange looking diagram that's here is what's called a chromatogram, and you can see that word right here, chromatogram. And it basically is showing us all the different compounds that are in this particular crude oil, which is, again, a North Slope crude, okay? Each one of these peaks, each one of these little things that you see here, these little needle-like points, is a different compound. It's a different compound that's in that crude oil. Crude oils can have several hundred compounds in them, all right? And the relationships of these different compounds to one another, how much of one compound is there versus how much of another, that all dictates the characteristics of the crude, okay? So if we want to analyze the crude oil, we'd put it in a machine called a gas chromatograph, and we would be able to look at these peaks and analyze them and try to tell what the compounds are. So what are all these compounds? Well, when we look at crude oil, it's a range of compounds, okay? And they all look odd. In this diagram, as you can see, there are various colors. What I really want you to look at here is the colors, okay? So all those black colors are carbon, okay? They're all carbon atoms. All the light blue ones are hydrogen. So the two major components are carbon and hydrogen, all right? And then you can see every once in a while one of these little yellow guys, that's a sulfur, okay? And if I had here a Louisiana crude, Louisianas are sweet crudes. They have very little sulfur in them, okay? So the sulfur content differs. And then every once in a while you'll see one of these little red dots. That's oxygen. You can see there's very little oxygen in here. It's mostly the carbon, the hydrogen, and some sulfur. And there's some, every once in a while, there's even some nitrogen, okay? But the main things are the carbon and the hydrogen. And this table shows you that about, if you have a gram of crude oil, about 83 to 85% is carbon. That's the heart of it. Right? Because remember, this is logical. They came from cells, and most of what we are as cells and sea life is as cells is carbon. Carbon and hydrogen. We're made up of organic molecules, and that's what an organic molecule is. So you got a lot of carbon. You have about 10 to 14% hydrogen, and then the rest of the stuff, as you can see here, is relatively small percentages. Okay. Now, the carbon and hydrogen are in different forms. There are different types of molecules. So as you can see on this side of the table, there are basically 4 types of groups of compounds in crude oil. There are these things called the paraffins, now notice this is a funny little word here, the naphthenes, the aromatics, and the asphaltics or asphaltenes, okay? And you can see that by and large, most of it is paraffins and naphthenes, and a little bit of aromatics, and a very little bit of asphaltenes. Okay, so what are these compounds? Well, obviously you don't have to know all of this, but this is important, and trust me, next week it's going to be important when we think about how this behaves in water. So the paraffins, okay, which, as you remember, make up about 30% of the crude oil, they have the carbon bonded to the hydrogen in single bonds, okay? So the carbon is bonded to those hydrogens and to other carbons with just a single bond, all right? And some of them can be branched. See, these are branched, and these are kind of straight chains. And some of you may know methane. Methane is a paraffin, okay? It's a big component of natural gas, which oftentimes is associated with crude oil when it's in a natural formation inside in the earth. So these paraffins are very simple, straight chains, single bonds, okay? The next thing are the naphthenes, and they're about 49% of what's in there. And these are a little bit different, okay? Now notice they still have those single bonds of carbon and hydrogen, but now they look like a ring, okay? So they're more cyclic. We call them sometimes cyclo. You'll see a term used sometimes, cycloalkanes and things like that. But they're in a circle, so you don't have those free ends. And that's going to have some ramifications for, again, what happens when crude oil gets into water. Then we have the aromatics, okay? Aromatics are only about 15% of the crude oil, but they're very important constituents because of some issues regarding how easily they break down in water and their toxicity, okay? So here are typical aromatics. The difference now is that some of the carbons have double bonds between them, okay? And they tend to be in rings. So notice they're rings just like those naphthenes were, but they have these double bonds between some of the carbons. And if you think about this, okay, I'm a sailor. I like wooden boats, okay? And if I want to go out in a wooden boat, I have a wooden boat. It's not very big. It's only about 21 feet long. But it's built like a tank. And it's got a lot of really tight linkages between the deck of the boat and the base of the boat. And there are all these little connections that are made that are paired together, so that there are a lot of tight bonding between the deck of the boat and the keel of the boat with all of these pieces of wood. And it's just like an aromatic. It's tough. It's hard to break. All right? Hard to break down these things. So there are two kinds of aromatics. There are what we call the single rings. See, there's only one ring there. And then this compound, which is called naphthalene, has two rings. Okay? So sometimes you'll see these multi-ring ones called polycyclic aromatic hydrocarbons. And you're thinking, oh my gosh, this woman is a crazy person going on about this on a Saturday afternoon or Saturday night for me. PAHs. But let me tell you, next week PAHs are going to be important. These compounds are monitored because they tend to be very toxic and they tend to behave differently in water than some of the other compounds. So these are the multi-rings, polycyclic, many-ringed aromatic hydrocarbons. So when you see these things, they have a lot of these double bonds in them. They're like tanks, very hard to break apart. Okay? Here's a typical North Slope crude. This is looking at the concentration of a bunch of different PAHs, those polycyclic aromatic hydrocarbons in a North Slope crude. And you can see there are, even though this is only 15% of the crude oil, they still are in very, very high percentages, some of them, and they can be really problematic. We've been doing a study here at UNH looking at the biodegradation potential of these of some of these PAHs, particularly some of these naphthalines down here, which are really highly present in crude oil. And we've been looking at their solubility and how long they take to break down in seawater at 5 degrees, at 0 degrees, and at -5 degrees centigrade. So these compounds are really important because they tend to stick around and they tend to be very toxic. So any questions on the characteristics of these compounds that make up crude oil? I'm going to check in with Barrow. How are you doing over there? Can we put on the sound?
We are good.
We can hear.
You can hear? Do you have any questions?
Yes.
You have a question?
No. No, I don't think so.
Is this
Until
going
further
too
notice.
fast or too fast or too slow, or is it okay?
I have a question.
Yes.
I have a question. Can you hear me?
Yes, yes.
Through the refining process, do these various iterations of crude oil become more toxic as they're more refined?
Okay, here's what happens when they're refined. Let me go back to that picture of the refining, okay? And basically, what happens is the different fractions tend to come off, those different compounds come off at different temperatures, okay? So the things that are lots and lots and lots of those ring compounds, they tend to be very, very heavy, especially if they have a lot of carbons in them. Some of these things can have 35, 40 carbons or more. And so they tend to be in these heavier fractions, okay? Now, the questions of toxicity are quite complex. I'm not sure that we're actually going to get into those in any detail next week. Maybe if we talk to David and we end up doing more in this series, we can talk about that. But the key thing is that what these compounds differ in toxicity, but they also differ in the size. So, in other words, the things that are going to come off up in here, in these higher fractions, are going to have fewer carbons, okay? They might have some rings, but they're going to be lighter and they're going to be fewer carbons, all right? And so the question of toxicity really then begins to relate to how available they are to getting to the organism, okay? So it's kind of complex, and I don't want to go confusing, and I can't answer your question directly right now because we don't have enough information. Next week, we'll talk about how these different things behave when they hit water. And some of these heavier fractions, if you just took the compound itself, it might be very toxic, but it's not going to move as much because it's very dense and heavy and it's going to stay kind of as a blob. I'm not sure that answered your question, but it's a complex one that you've actually asked there. Do you want to ask it? Yeah, is that okay?
I was just thinking in relation, I used to do boiled wildlife response down in the San Juan Islands of Washington and wasn't really sure if you have an oiled seabird or a seal, which one of these is going to be the most toxic, some because it's going to have that suffocating effect and some because of the chemical makeup.
Yeah, and that's the key. You've nailed it right there. So they're really, when we talk about toxicity, we have to think about the method or the mode of exposure, okay, and the length of exposure. So maybe we'll make that if there's interest, obviously I'm not trying to do anything that people aren't interested in, but we could do another one on toxicity and talk right about those issues. Okay?
Thank you.
Okay. Any other questions from any of the other sites? Doesn't look like it. Okay, so we'll continue on then. Okay, so the next thing I want to talk about is characteristics of crude oil. And this is going to be something where you're going to shake your head and say, oh, this crazy professor, why is she talking about this? But you're going to see when you start going out and looking at how people respond to oil spills, they're going to start talking about some of these characteristics. So I want to go over them with you because they dictate how crude oil or any of the products refined from crude oil will behave in the water, okay? So we'll go through some of these. The first thing is the density, okay? And you probably remember density from maybe from college or high school or whatever. But the density of something basically tells you the mass, okay, per unit volume, okay? It's the mass of the substance per unit volume. So, for instance, the density of water is 1 gram. This is water, okay? This is fresh water because I'm going to give you seawater in a minute. Is 1 gram, approximately 1 gram per milliliter or cubic centimeter. Now, just in case you don't know what a milliliter looks like, okay, I've got a little bit of a milliliter here. Well, I do have a milliliter here of oil. Oops, and you're not going to see this very well either. So we'll try coming a little closer. See that vial there? How's that? That little amount of blue in the bottom is a milliliter. It's not very much, okay? It's what can fit in a volume that's 1 centimeter by 1 centimeter by 1 centimeter, a little less than a ½ an inch by a ½ an inch by a ½ an inch. And if we actually look at fresh water, the actual density at 60 degrees Fahrenheit, okay, so I picked a Fahrenheit temperature that maybe you could relate to, is about 0.9999 grams per milliliter. Okay? Now that might seem to you, I don't know what that is, right? Well, let me give it to you in another number that maybe you can relate to. It's about 8.34 pounds per gallon, okay? So if I had a gallon of water here, it would weigh about 8.34 pounds. That's its density, 8.34 pounds of water, grams or pounds of water, per gallon, okay? But we don't usually talk about pounds per gallon. We usually relate it in grams per milliliter or grams, sometimes you'll see per cubic centimeter, all right? So that's fresh water. I picked out some things that I thought you might be interested in to compare that for densities. For instance, whale oil, all right? So at 60 degrees Fahrenheit, a typical whale oil has a density of 0.925 grams per milliliter, okay? So if you had a milliliter of whale oil, density about 0.925. A little bit less at 60 degrees, right, than that water, all right? So what that means is that the whale oil will float on the water, okay? Now, let's talk about some other things that maybe are of interest. All of these are, again, at 60 degrees. So if we look at a gasoline, okay, if gasoline gets spilled on water, its density is about 0.74 grams per milliliter, okay? So gasoline is really light, and that's to be expected. Remember where the gasoline came off on that refinery thing. It was very high, very light, the lightest stuff, okay, except for the gas, and it's going to really, really float on top of that water, okay? All right, how about some crude oil? Okay, now remember I said crudes are different. Here's an example. If we look at a typical North Slope crude, it's about 0.87 grams. These are all at 60 degrees again. It's about 0.87 grams per milliliter, okay? Same as Texas crudes tend to be about that. If I go to Mexico, the crudes are a little bit more dense. They're a little bit heavier, okay? And so this is a North Slope crude. If I go to a Mexico crude, that's going to be about 0.97. See, it's a little bit more dense. So it's floating on top of the water, but it's getting very close to being the same density as the water, okay? So that's the concept of density. Now, a couple of other things I want to point out about density. Just in case you say, well, we're up here with seawater. We're not with fresh water. We have a lot of seawater. The density of seawater is about, this is full strength seawater, is about 1.024 grams per milliliter. So look, that's more dense, and that's everybody knows that, right? I'm sure you guys know that much as well as I do from being on the Arctic Ocean. So the density is higher in seawater than freshwater. So freshwater is going to float on the seawater, okay? So the other thing to note is that density, I'm very sorry here. I keep hitting the wrong thing. Density changes with temperature and pressure. Okay? So if the water is at 0 degrees, or 4 degrees centigrade, the density is very, very close to 1. It's actually this very, very close to 1. In fact, it is pretty much 1. As the water gets warmer, the density goes down a little bit, okay? So temperature can change density. All right, pressure can also change density. If we have a lot of pressure, it's going to make the thing more dense. But most of the time, for the spills, we're thinking about stuff on the surface, and so the pressure isn't as great. Now, that was obviously different for the Deepwater Horizon, where the pressures were much greater because it was very, very, very deep water. Okay? So, that's the concept of density. All right? How dense is something. Now, when we start talking about crude oil, people don't talk about density. You're not going to hear them talking necessarily about density. They're going to talk about potentially specific gravity, okay? So all of a sudden, things are going to not be densities, which is a term you're familiar with, okay? All right. Specific gravity is basically a ratio. That's all it is. It doesn't have any units because specific gravity is relating the density of whatever it is you're dealing with, in our case, oil, to the density of water. It's a ratio. It tells you how dense the oil, in this case, the crude oil, you can do densities, you can do specific gravities for a lot of things, but we're obviously concerned with oil. Specific gravity of the oil and water related to one another is the density of the oil over the density of the water. Okay? Now, if we think about it, here's what's going to happen. So if we think about that North Slope crude, so if we use your North Slope crude, okay, and we do it at 60 degrees centigrade, 60 degrees Fahrenheit, pardon me, we're going to have 0.87 divided by, and let's use, instead of fresh water, let's use seawater. So divided by 0.1024, okay? That's the specific gravity of North Slope crude to seawater at 60 degrees. And in this case, it's about 0.84, all right? What that tells us is if the specific gravity is equal to 1, then the specific gravity of the substance is the same as that of water. So they're going to mix. If the specific gravity is less than 1, if the specific gravity is less than 1, then the substance is going to float on the water, okay? So in this case, that North Slope crude is going to float on the water, okay? Now that's great, but here's the problem. When you go look up an oil, or when you see people who are in the oil business talking about oil, they don't talk about specific gravity either. They talk about the API gravity, okay? So you'll see this API term floating around. Actually, that I shouldn't have said floating around, but you know, you'll see this term API. It stands for the American Petroleum Institute gravity. All right, this was developed by the American Petroleum Institute. Okay, now, what does that mean? Okay, the API gravity was basically a term that's created. It's a function of specific gravity, okay? But nobody wanted to be talking about these funny numbers like 0.84, right? They don't like to talk about those kinds of numbers. They want to talk about whole numbers that are greater than 1. So they made a formula that basically tells you about the specific gravity of the crude oil or the product. In this case, crude oil is what we're talking about. Okay, so what is this API gravity? Okay, it's a way to express specific gravity. It's a way to tell us whether something's going to float on water or it's going to sink. Okay, all right. So here's the formula. It's 141.5. I didn't make this up. This is really what it is. Divided by the specific gravity minus 131.5. Okay? These are very strange numbers. But here's how this is going to work. All right. Now, if we think about it, let's put in here a specific gravity of 1. Okay? Now, what does a specific gravity of 1 mean? It means that the specific gravity of the substance, whatever it is the exact same number as the specific gravity of water, right? So if water has a specific gravity of, let's say, 1, and the specific gravity of the substance is 1, guess what? This number is going to be 1. And then what we're going to have is the API gravity is equal to 141.5 minus 131.5. And so the API gravity is going to equal 10. Okay? And that's the magic API gravity number. So when you go and look up crude oils, you'll see API gravity numbers. And sometimes they'll just say API, and then they'll give a number. Okay? Unitless. All right. What does this API number of 1 mean? Okay. Of 10, excuse me, mean. Okay. Now, If you have a substance that has an API gravity less than 10, it's going to sink. Okay? It's definitely going to sink in water. Okay? If you have an API gravity for your crude oil that is greater than 10, it's going to float. Okay. Now, the closer your API number is to 10, the harder it is to distinguish what it's going to do, sink or float. Okay? So the closer that API gravity number is to 10, it's going to be hard for us to predict whether it's going to sink or float because, it could go either way. Okay? It's like a close election, right? It could go either way. The range of API gravities that you'll see are from 70 down. 70 is the absolutely lightest stuff there is. Okay? It has specific gravities that are much less than 1, and this is the stuff that really, really floats. Okay? So when you go and look at a different oil and somebody says, oh, this is an oil that's an API of 70, it means where it's a product that's an API of 70, it's really, really, really light, and that stuff's really going to float. Okay? The closer that API gravity gets to 10, the less it's going to float, the less easily it's going to float. It's still going to float. And then if it goes below 10, it's going to sink. Now, you may say, well, why is she making such a big deal out of this, right? Well, the answer is that sometimes during a spill event, if particles get mixed in with the oil, okay, sand or something like that, a lot of the waters up in the Arctic, especially at the outlets of rivers, are very turbid. You put a little bit of sand or a little bit of particle, clay-like material in there, and that can just tip that oil to be a sinker, okay? Because you've added a little bit more density to the oil by mixing those particles in, and it can now go from an API gravity that's lighter, maybe 20, and become a sinker, okay? So that's why it's going to be important next week what these numbers are. Everybody set on that. Okay. Let me just go back and make sure everybody is set on that because that's going to be important. Any question? Any questions from Barrow?
Can you hear me?
Yes.
Ron,
You have a question?
for the record, I'm a substitute partner.
I'm sorry. Could you say it again?
You look closer, I'm sorry. Ron Sagana, for the record, I'm a subsistence hunter.
Yes, sir.
Say they get further down the road, they get this offshore drilling rig going, and besides where they're drilling up the oil, say somewhere, however big of the radius, oil starts seeping out of the ground, and it gets a little too late for them to recover that. How long, or however many years or decades, will it take our ecosystem to get back to normal, if it does happen?
Oh, that's a very difficult question to answer. I know you want an answer right now, but if you can just wait a little bit till we talk about this, because you see, it depends a lot on when the oil and how the oil enters the water, what type of oil it is, and whether it sinks or floats. And you're going to see some other properties here in a minute that are going to be important too, whether it goes up in the air or it goes into the water. So it's real complex, and we can keep going and get eventually to that, but that's several talks down the road, okay? I know you want an answer right now, but it's
Okay.
very complex, okay? I'm not trying to dodge it. I'm just trying to get,
I
Okay.
understand that.
okay,
Affirmative.
affirmative, okay, thank you. Okay. Now, another thing that is big in oil, remember I showed you that there's some sulfur in it. There's not that much. It's usually less than 1%. But the sulfur is something that differentiates different crudes. Okay? So sometimes they talk about the sulfur content. And that's just how much S is in the organic molecules. All right? And one of the factors for the S is when you burn it, how much air pollution it makes, certain kinds of air pollution, sulfur-based compounds. But we're concerned with the sulfur because it's going to tell us something about the crude oil. So if somebody tells you it's a Louisiana sweet crude, it doesn't have very much sulfur in it. Okay? And we're going to see that's linked to some other properties. So this diagram right here shows you some crude oil, okay? Now, when crude oil is formed, it's over geologic time, right? And so when you think about it, it's not going to be a static thing. It's happening in the earth, and stuff is happening to change that crude oil. Some crude oil contacts with natural gas that's underground as well. And when that happens, when the crude oil mixes with natural gas, the crude oil changes. So that's why in some reservoirs, when we drill into them, they have a different kind of oil, right? It's still crude oil, but that crude oil isn't going to have as much sulfur in it, and it's also going to have an increase in API gravity. Now, what would you think that means? Normally, if I saw an increase in API gravity, I'd think, heck, that stuff's getting heavier. But no, it isn't, is it? Right? Because remember, API gravity the numbers are just opposite of what you think. 70 is a much lighter. It's a much more of a floater, remember, than a 10 or less. So if it has a higher API gravity and less sulfur, it's sweeter, it's lighter, it's going to float more, okay? So we tend to see that kind of oil in formations, in reservoirs, where we've had a lot of contact with natural gas. Now, older oils where there's been a lot of heat and a lot of thermal interaction, a lot of heat changes to the oil once it's formed. Those also have very high API gravities. They're very light, those crudes, and they have much, much less sulfur. That's the Louisiana sweet crudes. That's what we get in Louisiana, okay, in the coastal areas of Louisiana. And then if the crude oil underground has interacted with water a lot, it's got a decreased API, which means it's getting to be towards a sinker, and it's got much more sulfur. Okay? So what happens to the crude oil once it's formed while it's underground and interacting with things can really change its properties. Okay? That's how you get different types of crudes underground. Okay. Now, we're going to make these slides available on our website so you can actually download them on your computer as a PDF so you can see them a little better. But what this graph shows you over here is the sulfur content, how much sulfur there is in the oil. Okay, this is the sweet stuff. It has little sulfur. This is 0% sulfur. This is about 3% sulfur. This is what's called sour. Okay? And then over here is the API gravity. And here's the low numbers. So this is the heavy stuff. And here's the high numbers. Here's the light crudes. Okay? So let's look at some of these. Here's that Louisiana sweet crude right there. It has a density, an API gravity number rather, that's about 37 or so, 38. And it has a very, very low sulfur content, hence the word sweet crude. All right? When we look at some of the crudes from Mexico, remember I showed you that crude that had a specific gravity that was about 0.9, and I said it was from Mexico? They have very heavy crudes there, okay? So the crudes are heavy, API gravity is low, and they got a lot of sulfur in them. So they're going to behave differently in water, all right? And you can see that there are a lot of different relationships here for the different types of crudes that are found around the world, okay? This Mars site right here, this is off in the Gulf of Mexico. It's an offshore drilling site in the Gulf, and you can see it's tending towards a little bit heavier crude. The API number's less than 30, and it's got quite a bit of sulfur in it. So again, it's a function of how that crude, once it was formed, started to interact with the natural environment in the subsurface, whether it was heated up a lot, whether it came in contact with natural gas, or it started to have some interaction with water. And that's going to dictate what the crude is like. Okay? Now, another thing about crude oil that we characterize it by is its viscosity. And everybody knows what viscosity is, right, pretty much. I mean, it's how easily it pours. Actually, when we were defining viscosity in science terms, we're thinking about how fast it moves over a certain area and a certain distance over time. And the way I like to think about this is, you know, some of those crudes that are very, very viscous are more like molasses. But where viscosity really comes into play is when we think about the refined products. So the gasolines, very low viscosity. Those heavier products that come off in the refining, very, very high viscosity. We've been doing a little bit of work looking now at some of the oil sands products that are coming out of Alberta, and those are what we call bitumen. So they're different than a crude oil, okay? They're bitumen, and they are very, very, very heavy, and they are very viscous, okay? So they're really, really, really viscous. So there are lots of different things. But viscosity is going to tell us, when we say this oil is very viscous, is how it's going to move. Okay? Here's the relationship between density and viscosity. There is a relationship. So here's density. This is going to more dense stuff. And here's the viscosity. The viscosity is going up. So you can see here, here's our light oils, here's our bitumens and our heavy oils, and look at that. As the density goes up, the viscosity is tending to go up, and it really goes up big time, the viscosity, because if you look at this scale, this is 10, this is 100, this is 1,000, and this is 10,000, and this is 100,000. It's what we call a log scale. So as the density increases a little bit, the viscosity really shoots up, okay? And this stuff, bitumen, oh my gosh, that stuff's really tough to move. This next one, and we're almost done now, is volatility. This is how the stuff likes to go into air, okay? How volatile it is, how much it likes to go into air. All right? And you may think, oh, this is not that important. But it is, because when you're addressing a spill, if you have very, very volatile fractions, they're going to tend to go up in the air and not be in the water. And you'll see that next week. This concept of how much it has an affinity for going up in the air is very, very important. And we relate this to the things, to the crude oil's boiling point. Okay? The lower the boiling point, the more likely it is to go up to the air. All right? Here's an example of that. Here's boiling point over here. So as boiling point increases, here's the number of carbons in the compound. Here we have benzene. If you went and pumped gas into your car today, you might have seen some vapors coming off, okay? Those are the light fractions of the gasoline. They have very, very low boiling points, so even on very cold days, you can see them, and you can smell it. Very light, very few carbons. Goes into the air rapidly, going to evaporate quickly during a spill. May cause air problems, may cause problems for the responders and for the public, okay? Whereas when you get carbon compounds that have lots and lots of carbons in them, those very big ring structures that we talked about in the beginning, those aromatics that are all sorts of rings together, look at those babies. They have very high boiling points. They're going to be gloppy. They're going to stay where they are. They're not going to go up in the air very easily. Okay? And you can see that here. The gasolines, the kerosenes, they have more of these lighter fractions, fewer carbons, low boiling points. So stuff's going to go up in the air more easily than these lubricating oils, these heavy, waxy types of oils. Okay? Components from the oil. The last thing I'm going to talk about today is solubility. Now, when I was a kid, there was a saying that says, oil and water don't mix. Okay? And in fact, if I take some water here, okay, and I take some of my North Slope crude, and I put it in to this water, oops, wrong vial, you can see that that oil is floating on the water's surface. Okay? I'm going to get out from behind it so maybe you can see it. It's right here. It's floating on the water's surface. All right? That's because it's less dense, right? We could have predicted that from all of today's talk. It's less dense. The specific gravity is less than 1, and the API gravity is much greater than 10. So it's going to float. Okay? Now, don't be deceived. The oil and the water don't mix. I can try to mix them up, and we're going to see this in some videos next week. They don't mix very well. But there are some percentage of the compounds, those compounds that I showed you in the beginning of the talk, that actually dissolve into the water. Now, there's not a lot, but there are some. So solubility is what dissolves into the water. It's not a lot, but there's some. And there's a table, and again, we'll put these slides online for our website so that you can get a hold of them, and we'll make them available at the library too. What you can see here is that when we talk about some of these lighter fractions like the pentanes, those are those simple things that we talked about way at the beginning of this talk that just have a single bond between the carbons, just those nice little chainy things. Here's the solubility of those at 25 degrees centigrade, about 47 parts per million. What that means is about 47 milligrams of that pentane dissolves into a liter of water. Okay? Now that's not a lot. If I talk about sugar, I can get hundreds of grams, right? I can get easily 180 grams to dissolve. You know, I mean, you do this with coffee. If I make a thermos of coffee, I could add a lot of sugar. Dissolves. It's readily soluble. So it's true that oil and water don't mix, but there's some percentage of those, some small fraction of the compounds that will dissolve in the water. And it's those that really are going to be important in us thinking about what the impacts of the spill could be on the environment. Now, as the compounds get bigger, as we get more carbons, so as we get more carbons, and we see that the solubilities go down, okay? The more carbons, the less soluble. So we have here trimethylhexane, okay? So that has about, again, one of those single bond things, has a lot of carbons in it. It's only soluble at 0.54 milligrams per liter. Much, much less soluble. Okay? And then we have those rings. Look at the rings. These are really important. Benzene, these very single ring compounds, they have solubilities of about 1,700 milligrams per liter. That's about 1.7 grams per liter. That's a lot. Now, it's not the same as sugar or something like that, but that's a relatively large amount. Okay? So all of these factors that we've talked about are all going to influence how the oil behaves when it's spilled on the water. And we're going to refer back to them next week. Now, just in case you have a hankering to know about crude oils, you can actually go to this site that's right here. It's called crudemonitor.com, and it's a Canadian site. Unfortunately, they don't have any U.S. oils, but it's a really, really great site, which is why I mention it. So if we go to this site right now, and again, these slides will be available for you. Here it is, coming up. All right. This site gives you data on all sorts of crudes. So here, for instance, is a light sweet crude. You can click on this, and you can see the different light sweet crudes and where they come from. So this happens, these are all, unfortunately, this is a Canadian site, and there really isn't a good equivalent in the U.S. But you can also see all about the properties we've talked about, the density, the API gravity, the sulfur content, the different kinds of compounds that are in it, the different kinds of light ends, etc. And here's the other thing I want you to look at. Okay, let's look here at the API gravity over time. Now, what we've got along here, along this lower axis, is from 2002 to 2005, and so here at one end is 2002, here at the other end is December of 2012, okay? It's a 10-year span, and these are API gravities, and so this is the same crude oil coming out of the same formation over 10 years, and you can see that API gravity changes over time. You can see that the sulfur content changes over time, okay? I started off in the beginning saying a crude changes over time. A crude is different from one formation to another, depending on what kind of exposure it's had to water or natural gas or other heat. It changes as a function of lots of different factors. So crude oils are always changing, even out of a given well. Okay? So that kind of goes full circle to what we talked about at the beginning. So today, we've talked about my background, how this series was developed, the goal for this series, and we've talked about what crude oil is. Next week, we're going to talk about what happens when crude oil gets into water, if any of you are still interested in watching. I might be talking to no one next week, but hopefully some people will come back. So I'm happy to answer any questions that you might have, and I'm really pleased that you've stuck through this for such a long time. Questions? I think you have to click on the...
Oh, it's on already. I have two questions. When they express the type of oil in the commodities market, they usually say light sweet. Is that because it's easy to refine, or what is the difference between sweet and heavy? And my second question is, do they know? Oh, my second question is, do they know what the composition of the crude oil that Shell is trying to drill out of the Arctic? Is it different from the North Slope that's drilled from the ground from Prudhoe Bay?
Okay,
Thanks.
so the first question is about the light sweet, okay? And that really relates to this diagram that's up here now, all right? And the sweet refers to how much sulfur, whoops, I forgot to do something here. It refers to how much sulfur there is. So the less sulfur, the sweeter it is, okay? And here's a way to think about that. I don't know if you've ever smelled like sulfur and sulfide. It's stinky, right? So less sulfur is a sweet crude. It smells sweeter. Not that it smells sweet, by the way, but it's sweeter, okay? And more sulfur is a sour, all right? And so the other thing that tends to be the case is Louisiana sweet crude, which is right there, that red one that I'm circling right now. That is a sweet crude. See, it doesn't have very much sulfur in it, and it's relatively light. Its API gravity is around 37. So it's a light, sweet crude. API gravity, relatively high number, less sulfur. Okay? Now, the problem is you don't know exactly what you're going to get until you drill. Okay? So when the oil comes out of the ground, you characterize it. They characterize it for the sulfur content. They characterize it for the API gravity. They measure the gravity with some tests that are done. So until the oil comes out of the ground, you don't know the exact characteristics of it. All right? So I can't exactly tell you what they'll get, and I suspect that a company has some idea about what they're going to get, but until you actually drill that well, you don't know.
Okay.
And it really depends, going back, it really depends as to what happened to that oil, whether it mixed with water underground, whether it mixed with, had more thermal changes to it, or whether it maybe interacted with natural gas, as to whether it's going to have less sulfur and what its API gravity is going to be. So there are ways to predict based on what you think has happened in the geologic formation. But until you get that oil, you don't actually know those numbers. Okay? Did that answer your question?
Yes. Thanks.
Other questions there in Barrow?
No.
Okay. Are there questions in, it looks like the only one still left is that, oh no, I don't think that anyone else is paying any attention. So now let me ask before you go, was this interesting, or what would you like to change or do differently? Because next week I'm going to talk about oil and water, but I don't know if this was at the right level or bored you or what. Yes, go ahead.
Here's someone.
I thought it was fantastic, and I've been in the past involved with oil spill response, and in all of our trainings, this would have been really helpful. We talk about how to get out there and set the boom and currents and everything, but not enough about the properties of oil. And since I had that background, it gave me a really good context. And I want to hook you up with this organization so they can join in on one of these talks, because I thought it was really informative and very clear.
Okay. And if there's anything you want to change, I can't change oil, but I certainly can change the talk and the approach for next week. So if we just put the slides back up. And David will have this. This is my email. And you can email me if you have comments, things you'd like to change. And also that address that you see there, www.crc, that's where we'll have the slides posted if you want to get the slides that I just used, okay? And then you can look at them. And maybe you'll be able to see them a little better when they're on a computer screen in front of you. And we'll work with David to make sure that they're at your library there, maybe on a computer or something, so that you could see them if you don't have access at home. Okay? Any other questions or comments or thoughts?
You did a real good job of having it at a level that you don't have to be a college senior to understand.
That's because I have a very simple mind. I can't make it too complex.
Thank you.
Anything
Thank you.
else? Thank you for coming on a Saturday, and I hope to see you next week.